Welcome everyone. So my presentation was focused, as Jaap said, on the effect of heat stress on fecal microbiota composition in swine. And this project is part of the Feed Engine project, and it involved several teams from INRA in Rennes, Toulouse, and 2 experimental facilities from Surgères and Petitbourg in Guadeloupe. The livestock production is exposed to several environmental perturbations, such as ambient temperature elevation or some sanitary problems, which cause troubles on the performance of the animals, like decrease of the feed intake or decrease of growth performances. And in particular, heat stress is a main concern for livestock production in many countries, in temperate climates, in summer, for example, or in tropical climates. So the livestock production is looking for new methods to improve the performance of the animals. Because microbiota plays a role in the pig metabolism, it could be a good help for the host to better coping with the environmental perturbation, but we don't know yet if this microbiota is really involved in the decrease of performances in case of heat stress. And first, we don't even know if the microbiota is really affected by the heat stress. So that's the first step we want to answer. And the objective of this study is then to evaluate the impact of a climate or heat stress on pig gut microbiota. For that, we follow this experimental design. We use 1,200 pigs from crossbred large rat Creole. And these pigs were half of them raised under a tropical environment under chronic heat stress between weeks 11 and 23. And the other half were raised in a temperate environment under thermal neutrality around 24 degrees Celsius. For the pigs under temperate environment, at week 23, we increased the temperature to 30 degrees to expose them to an acute heat stress during 3 weeks. At the end of the 33rd week and 36th week, we collect fecal samples to evaluate the fecal microbiota using the aluminum MySeq sequencing, and this sequencing results in taxonomic units, operational taxonomic units called OTUs, that is the microbial composition. So with this design, we can compare these 2 climates, so evaluate the climate effect, or we also can evaluate the temperature increase effect. And this color I will following them along the presentation. So we followed this statistical pipeline, starting with the OTU table coming from the samples with at least 7,000 sequences. And we had, after a filtration step, we had 1,700 OTUs. So the first step of the statistical pipeline is just to see what's inside our sample, so some diversity analysis. Then in the second step, we run an unsupervised analysis, a principal component analysis. So we just plot the samples without knowing where they come from, and try to see if there is any difference according to the environment. And then the third time, we applied a supervised analysis. So this time, that's a sparse partial least square discriminant analysis. So we know where the sample come from, and we try to discriminate, to classify them with the microbiota composition. And it's a sparse selection, so we have a selection step to select the best OTUs that discriminate our groups using a lasso penalization. So coming to the diversity results, we don't really see the colors. Between the thermal neutrality and acute heat stress, we see that there is a bit more counts, so a bit more bacteria under acute heat stress, but it's not different from the chronic heat stress. Using the Shannon index, which is another way to evaluate the diversity, we don't see any difference between thermal neutrality and acute heat stress. but a slight difference with the chronic heat stress. So we don't have any clear difference in the diversity between our three environments. The principal components analysis, so we just plot our individual, and like we can see here, such just a big group. We don't see any difference according to the environment. But when we color the samples, we see that it starts to group according to the environment. On the first axis, we separate the animals under thermal neutrality on the right from the animals under heat stress on the left. And the second axis allows it to separate the two climates, temperate on the bottom and tropical on the top. So from an unsupervised analysis, we already start to see some differences according to the microbiota composition. So the discriminant analysis, so first here we try to separate the animals under thermal neutrality or chronic heat stress. And there is really a high discrimination using the microbiota information, and that's only with 36 OTUs, so very small number of OTUs allow discrimination with only 1.7% error rate. Using the two components, we have a bit more OTUs, and we see that these OTUs are mainly unclassified ones, or a quarter come from the Prevotelaceae family. When we want to separate the animals under thermal neutrality and the animals under acute heat stress this time, we also well discriminate these two groups using this time 32 OTUs and less than 10% error rate of this classification. And this time we also have mainly unclassified OTUs, but also Prevotelaceae and Lactobacillus. When we compare these two discriminant analyses, we try to extract the OTUs that are biomarkers of a temperature increase. And we find that there is 5 common OTUs, so only 5 biomarkers of this temperature increase. So this led to the conclusion that it seems that we have 2 different stresses. One is only a short-term temperature increase, and the other one mostly related to a tropical environment, so more global with temperature, humidity, etc. So according to the conclusion, we've shown that microbiota information can be used to discriminate the animals according to different climates, or pigs exposed to heat stress or not. The microbiota composition can then be used as a biomarker of the exposition to a heat stress, especially in our experimentation. And now the question remains, because the microbiota is different according to this environment, is it possible to use it as a biomarker of the heat stress, of the adaptation of the animals to the heat stress? So this question remains, and further studies are ongoing to try to answer to it. Thank you for your attention.
Thank you, Mathilde, for this nice presentation on microbiota. Questions? Several.
Thank you for the nice presentation. What's your thought about, because I assume that between neutral temperature and chronic heat, or the heat stress, you have differences in feed intake. How do you account for that? Because I assume during heat stress the feed intake decreased markedly, no?
Yeah, for now I'm just this first step just focused on the microbiota composition without looking at the performances at all. The second step will be to try to mix the two ones to see if there is any link between this intake, this feed intake, and this microbiota. For now, I'm sorry, I don't have this answer. Yeah.
Thank you for the presentation. I just was wondering if in the future, are you also considering to have prediction of the functional profile of the microbiota as well, because as you show, apparently there is not different at compositional level, at least in the area of the presence or absence of the bacteria, because you didn't see any difference in the alpha diversity index. So probably the most important difference are in the abundance of the OTUs, or even better in the functionality related with the response of the microbiota to the heat stress.
Yeah, we plan to do that using the KEGG orthologs. For now it's ongoing, I don't have the data yet, but yes, we plan to try to relate this microbiota information to functional biological functions, yes.
You see, two enterotypes have been described for the pig. Have you tried to look if it's possible to stratify the pigs according to various enterotypes or not?
Yeah, I tried this, and I didn't find the result I was expecting, because I can't classify my pigs according to these enterotypes, actually.
Other questions? Again, we can ask some more questions if you'd like during the panel discussion. Thanks again,
Thank you.
Mathilde.